It's probably going to be a bit of a longer video, and it has to do with section 5, 6 in our textbook. A lot of constructing polynomials and then breaking polynomials down into their linear factors and finding the roots. So we're going to start with constructing a polynomial with the roots -1, 2, and 5. So it's kind of like we work backwards and we start with our answer of x equals -1, or x is 2, or x is 5, and we're going to work our way backwards. So instead of solving for x, we're going to kind of work backwards. So if I add 1 to both sides, I'll get x plus 1 is 0. And then if I subtract 2 from both sides, I'll get x minus 2 is equal to 0. And then finally, if I subtract 5 from both sides, I'll get x minus 5 is equal to 0. Okay? And then we're going to go backwards from the zero product property. Each one of these is equal to 0. And I'm going to multiply these three factors together. I have x plus 1, x minus 2, x plus 3, x minus 5, excuse me. And then we're just going to work all the way down, and we're going to get what the original polynomial looked like. We're going to FOIL x plus 1 times x minus 2 in red, and it says FOIL, or it's underlined. So we'll go ahead and FOIL that. Okay, and now I'm going to use the distributive property, and I'm going to do x squared times x squared times minus 5, negative x times x times negative 5, and negative 2 times x, negative 2 times negative 5. So that's what's going on here. Maybe you can pause it and try doing it on your own, and then you can double check. And then what I'm going to do is I'm going to combine my like terms. So x cubed's all alone, but I got some x squared, so I'm going to combine them, and I got some x's, and I'm going to combine them. And that's what my original problem would have looked like, and we'd have to use something like the rational roots test, or theorem, to break down and find my three roots. So we're just going backwards. So I'm going to do one more example of these. I'm going to construct a polynomial that has roots I and negative I. So remember, I squared was going to be equal to -1. So we'll start in the same way. We start at the beginning. X is equal to I, or x is equal to negative I. For the first one, we'll subtract I from both sides. We'll have x minus I equals 0, or we'll add I to both sides. X plus I equals 0. And combine those two factors. And then we'll go ahead and FOIL. And then we'll make note that I squared is -1. Notice that we have like factors of Ix and negative Ix, so those are going to cancel out. We're going to be left with x squared minus -1, because I squared is -1, so we have x squared plus 1. And that's what our original problem looks like. Alright, let's move on to some other stuff. We have a theorem that complex roots come in conjugate pairs. So to remind you of a conjugate, if we have a plus bi, its conjugate is a minus bi. So the outside numbers are going to be the same, you're just changing the sign in the middle. Okay, so I'll give you a couple of examples. So we'll look at finding the conjugate. So we have I, 3 minus 2i, and minus 2 plus I. So if you want, you can pause the video and you can double check. The conjugate of I is negative I. And one way we could write that is I is the same thing as 0 plus I, so the conjugate would be 0 minus I, and that would be equal to negative I. Okay, so complex conjugate of I is negative I. Complex conjugate of 3 minus 2i would be 3 plus 2i. And the complex conjugate of -2 plus I would be -2 minus I. Okay, so the outsides are the same, you just change the sign in the middle. Okay. Alright, so let's suppose a polynomial has roots I, 3 minus 2i, and 2 plus I, what are the remaining roots? There might be others, but based off this information, I can tell you 3 more. So complex roots come in conjugate pairs. So we just found the conjugates of I, 3 minus 2i, and negative 2 plus I. So we can just write those conjugates. Those conjugates will also be roots. So negative I, 3 plus 2i, and negative 2 minus I would also be roots for this polynomial. We have no idea what it is, but we at least know it has 6 roots. So it's a 6-degree polynomial, and it would be a big mess to try to construct it. All right. So we're going to use this idea that complex roots come in conjugate pairs to kind of help us out with some problems. So let's say we're given that 5i is a root of this polynomial. And what I would like to do is find the other remaining roots. So we're going to get one of them for free. We're going to get negative 5i. Negative 5i is the conjugate of 5i. So we get one of them for free. This is a 3rd-degree polynomial, so we'll have at most 3 roots. So 5i is a root. And what I suggest for doing these problems is when you're given a complex root, find the conjugate, and then go ahead and find what the factor is. So 5i is a root, and negative 5i is a root. Then that means that x minus 5i and x plus 5i is a factor, and that's by the factor theorem. If c is a root, then x minus c is a factor. All right, we're going to go ahead and FOIL this out. You can FOIL it out on your own. I'm going to skip a step and say that it's x squared plus 25 because we have a limited amount of real estate on the page here. Okay? So if x minus 5 is a factor and x plus 5 is a factor, then their product will also be, in this case, a factor. Not always the case. 2 factors. Anyway, I'm not going to get into that. Anyway, x minus 5, x plus 5i, they're both factors, so their product should be a factor at this point. So I'm going to just mention I FOILed, and then that's a factor of x cubed plus 3x squared plus 25x plus 75. Okay. X squared plus 25 is not linear, so we can't use synthetic division. We're going to have to use the old long division. We know that it's a factor, so it's going to divide into the polynomial evenly, which means it has a remainder of 0. So x squared plus 25 into x cubed plus 3x squared plus 25x plus 75. All right. X squared times x will give me x cubed. And then 25 times x will give me 25x. And it looks like this didn't quite come out as a 3, so I'm going to make sure this looks like a 3 here. Well, let's erase it and we'll make it look like a better 3 here. Come on. All right, that looks like a better 3. All right, go ahead and subtract. Bring down your other terms. X squared times 3 will give me 3x squared. And 3/4 is 75 cents, and we get a remainder of 0. Okay. So our other factor is x plus 3. So I'm going to go ahead and write this in what's called factored form. X plus 3, x minus 5i, x plus 5i. So this would be factored form, and actually the fundamental theorem of algebra and a corollary or two will say that any polynomial can be broken down into a product of linears over the complex numbers. So we can't do it over the real numbers, but we can do it over the complex numbers. Okay. So my roots will be, from the x plus 3, I'll get negative 3. So my roots are negative 3, 5i, and negative 5i. Okay. I have another one that's a little bit more complicated, but I think I'm going to make a separate video for that one. All right. Let's find all the roots of this polynomial. And we're going to write it in factored form, so that'll be just a product of linears. Okay. Now this time they didn't tell me what one of the roots was. The last one they said, hey, by the way, 5i is a root. They didn't tell me that. So what I need to use is I need to use the PQ theorem or the rational roots theorem to find my potential roots. So all the potential factors of 32, 1, 2, 4, 8, 16, and 32. Potential roots of the leading coefficient is just plus and minus 1. So all my potential roots are just all the p's there. Now you have to do a little bit of guess and check, but I suggest trying 1s and 2s and negative 1s and negative 2s when you're doing the synthetic division first. So I went ahead and started with 1, and I wrote down the coefficients of my polynomial. So 1x to the 4th plus 1x cubed plus 14x squared plus 16x minus 32. So we just wrote in those coefficients, and we'll go ahead and do the synthetic division. 1 comes down. 1 times 1 is 1. 1 plus 1 is 2. 1 times 2 is 2. 14 and 2 will make 16. Oops. We'll make 16. 16 times 2 will be... 16 times 1 will be 16, excuse me. 16 plus 16 is 32. 32 times 1 is 32, and then we have a remainder of 0. So what's left over is x cubed plus 2x squared plus 16x plus 32. And I also know that x minus 1 is a factor, and we can use the remainder theorem and play the same game again. So I do know that x minus 1 is a factor. And I worked this one ahead, so I tried negative 1, and it maybe didn't work, and maybe I tried 2 and it didn't work. So then I'm going to try negative 2. We have a lack of real estate. We'll do the synthetic division again. And I get a remainder of 0. Okay, so then that means that x minus negative 2 or x plus 2 is a factor because I had a remainder of 0. And then what's left over is an x squared plus 0x plus 16 down here. And this is going to give me roots of 1, negative 2, and then I have to solve x squared plus 16, so that's going to give me plus and minus 4i. And now I'll write in all my roots, and then I'll finally write it in factored form, which is just x minus each root. So x minus 1, x minus negative 2 is positive 2. X minus 4i and x plus 4i. So that's it, completely in factored form. So over here where you're doing all this rational roots business, this might be a little bit messy because 32 had a whole bunch of factors, but if you keep it small with 1s and 2s, usually you'll break it down enough, so you don't have to do too much. Alright, now let's move on. So we're going to talk about a concept called multiplicity. When we say it, multiplicity of a root c is the number of times n x minus c is a factor. So I'll give you an example. Let's say we went through and we factored something. Okay, x minus 1 squared x plus 2. And I'm going to say 1 has multiplicity 2. So if I went through and I solved x minus 1 equals 0, because I have 2 of them, I would have another one. So I get an answer of x equals 1 and x equals 1 twice. So that's where that multiplicity 2 comes from. I can eyeball it by just looking at the exponent there. Okay, so let's move all this junk off. Alright, now x plus 2 has an exponent of 1, so that just is going to have multiplicity 1. Alright. Now for the second one here, x plus 6, you have a 3 here, so that's going to have negative 6 as multiplicity 3. So how we're getting the negatives here is we're solving. And then we'd have x plus 9 equals 0. So we're setting each factor equal to 0. Okay. So because of that exponent of 3, 6 has multiplicity 3. And because of the square, x plus 9, the 9 has multiplicity 2. Alright. One more problem where we'll say, hey, I want you to construct this polynomial with this root and this root with multiplicity such and such. So let's write a degree 4 polynomial, so it'll have an x to 4th in it, with roots 2i and multiplicity 1 and a root of 3 with multiplicity 2. So because 2i is a root by complex roots coming in conjugate pairs, negative 2i will also be a root. So we get x plus 2i, x minus 2i. So that's your conjugates. And then we have x minus 3. If 3 is a root, then x minus 3 is a factor. Because it's multiplicity 2, we're going to have a square there. Okay. Now what I'm going to do is it's a lot easier to multiply the conjugate pairs together. You can FOIL that on your own. I think I'm going to skip a step and say it's x squared plus 4. And then you can FOIL out x minus 3 times x minus 3, and you'll get x squared minus 6x plus 9. And then we'll go ahead and distribute x squared times x squared times minus 6, x squared times 9. And then 4 times x squared, 4 times minus 6, 4 times 9. And then we'll combine our like terms, and after all that hard work, we have our polynomial. So working backwards from the roots, we constructed the polynomial that had those roots. Okay.